Hello everyone, welcome to another physical science lesson, and today we're going to be looking at some important ideas about how you can strengthen your thinking about physics. So I've called this lesson Thinking Physics. So when we talk about thinking physics, what do we really mean? The first thing is that we want to get an overview of what the physics content is all about. So what are the topics in physics? Well, the core knowledge is divided into things called mechanics. Then there's a section on waves, sound and light, electricity and magnetism, and some parts of matter and materials. Now, please remember that there's a lot more to physics than these topics that we do at school, but these are the important ones. And if you look at the structure of your curriculum, you'll see that in total, there are two that stand out that are really important. So mechanics and electricity and magnetism carry the bulk of your marks. So you really do need to have a good understanding of these. But apart from learning and knowing some details, you also need to grapple with some skills that can be asked in all of the topics. So what I want to emphasize here is the skills involve the design of investigations, representing relationships, application of principles to real-world situations, and they all lead in some way or another to calculations. So if we're thinking about physics, we have to recognize this as a fascinating subject. It requires lots of questioning and reasoning, and so it is very interesting. This is something that you should create some curiosity about. So look around you, look in the world, and ask questions about these things and see if you can apply what you're reading and learning about in class to real situations. So here is a question I would like you to consider. What is the best way to study and master physics? Well, you know, there are lots of different ways. People study in different ways, and we don't want to have a recipe, so to say, that everyone must do this. But there are some principles we want to bring out in this particular lesson to say, try these ideas, and here's some guidance to help you in your preparation and in the answering of questions. Because whatever you do, you're going to need to make sure that you have the kernels, the principles, to be able to solve the questions you're asked in your final assessments. So let's kick it off by saying, what's the starting point? And the starting point, like many other subjects, is we've got to have definitions. And this includes terminology. So if we recognize that there are words that we use in physics that are slightly different to the everyday words, we need to make a list of those and link them to the definitions so that we are very clear about what the meaning of critical words are. We also need to recognize that definitions link to formulae. And here's the important thing. When you're doing a formal assessment, those formulae are given to you. It's one of the advantages of this subject, is the way it's assessed, is that you can take with you, or you are given, a data sheet that has a whole lot of useful information. And here's a trick that I've learned, is even when I was at school, I was told, write down your definitions and annotate on a data sheet. It can help you then remember in the exam. You're not going to have everything written out on your exam sheet, but it will trigger for you the things that you will need to learn. So let's have a look at the data sheet. So the first thing is that there are a number of tables, and table number 1 deals with the physical constants. Don't be confused. You will get a data sheet that might not only be in English. This one's in English and in Afrikaans. But it is important to recognize what is written there. These are constants, for example, the acceleration due to gravity, little g, and it gives the units for that, the value and the correct SI unit. you'll see that there's a universal constant, big G. And so we could go through each of them. Recognize what each of these constants relates to. So this one relates to Newton's laws. So I'm going to say Newton. This one relates to the speed of light, and we can work out this. It relates to electrostatics. And so as you're going through, recognize what each of them relate to. And that's really important so that you can start to make meaning when you've got the data sheet in front of you. Try and make links between the constants and the formula. So table 2, which is written underneath that constant table, you'll see that they've got slight headings like motion and force. So you've grouped together your formula and you can see what they're related to. In the next part of the table, this is electrostatics. And then we've got electromagnetism, we've got circuits. And so it's very important that you take a note of each of the pieces of information. Recognize the formula. And as you're studying, what's important is that you start to annotate onto these sheets, onto this data sheet. Keep it on your desk, pin it on a wall, and every time you're adding a new topic, add writing to it. It will help you consolidate your information and your learning and help you remember. And then perhaps once a week or every second week, you take a blank data sheet and see if you can write everything down, all your definitions, all the formula, and you can annotate and recognize what's right. Now, in terms of using the data sheet, it's important that you identify vector quantities, that you recognize each symbol, and that you also learn the SI units for each quantity. And so it's creating those links that is very important for your ability to recall. And so I want to show you as an example. Go to the table again and recognize that we're going to be looking at vector quantities. You might say to yourself, what are vector quantities? Those are things that have magnitude and distance, direction, and we can always draw a vector diagram when we're answering those sort of questions. So if we go to the data sheet here and we're saying what are the things that are vectors, I might just make a little V there, or an asterisk with a V, because that's a vector, that's a vector. Time isn't a vector. Velocity is a vector, initial velocity is a vector, acceleration is a vector. And change in position is a vector. I go to net force, acceleration, force. Those are all vector quantities. What we need to recognize here is this is the force of kinetic friction. This is the force of static friction. That's weight, that's acceleration due to gravity. And so you recognize that there are vectors all over the place, but they're mainly in mechanics. However, there are some in electrostatics as well. So if you go to the next page, you'll recognize here is the force vector, and here is the electric field strength vector. So this is also a vector, and so we need to note it and to make sure that we've got it very clearly. Please note that in terms of electricity, we don't have vectors. There are no vectors here. In terms of the value of phi for electromagnetism, we recognize that the magnetic field strength is a vector, but we're doing a product there, multiplying them together. Phi is not a vector. Okay, so we are very clear about what is a vector and what isn't a vector, and that should be very clear in our heads. Every topic that has vectors, because when you come to check your answers in that section, you must check that you have a magnitude and a direction with the SI unit that is the correct SI unit for that value. Okay, so that is incredibly important. So as I've gone through these tables, please also note that perhaps in a different color, you're going to take note of the units. So we're going to say velocity is meters per second, acceleration meters per second, and we can go through that sort of process. The other thing is to identify formula, relationships with the formula, to identify what the constant is and to link them to the definition. So let me give you an example. This formula here is linked to Newton's second law. This formula here is linked to the universal law of gravitation. And so we can carry on and we can link the laws together and make sure that we understand how they link. In terms of the constant, you'll see that's the constant, which is capital G, and that's the little g from the values of the constants. So I hope you're seeing that this data sheet can be very useful in helping us summarize and pick things together and also link together. There is the universal law of gravitation, and we've got the units. Please notice that these units are compound units. It's not just newtons and something else. It's newtons, meters squared, kilograms to the -2. And so you must be very clear that you check the units of constant and recognize we can change things and check them in terms of, are they kilograms, are they meters, are they seconds? So for example, we can take newtons and we can say that is kilograms times meters per second per second. 1 newton is 1 kilogram times meters per second per second. So units help us very much to check that we're on the right track. And so in this sort of starting position, we're starting to think more like physicists. You know what? That thinking takes a little bit of energy. So why don't you take a short break, and we'll be back to support you in developing your muscles in physics. That is not your arm muscles or your leg muscles, but your brain muscles as we continue to think about physics. Welcome back to this lesson where we're talking about thinking like physicists, thinking physics. It's so exciting. And you know what? Apart from the first steps, it's all about engaging critical thought. And it's about encouraging questioning wherever you are. Not just when you're in the exam, when you're walking down the street, trying to relate what you've read in your textbook to what you're seeing in the real world. And so when we think physics, there are some critical thinking steps that we go through. To make our information real, we collect data. That's mainly through observation and experiment, and then we analyze or we organize the data. And organizing the data helps us ask more questions. And so in those questions, we try and form some ideas about what are the relationships that exist between variables or quantities. And out of that, relationships translate into formula or equations. And we can then perform those calculations and evaluate our answers. And that's very important. When you are checking and evaluating your answer, you've got to say, does this make sense? What would happen if I changed an input variable? Would it really make sense that as you increase that variable, another dependent variable is going to increase or decrease, or whatever the case might be? You've got to check, is this making sense? And of course, in your exam, make sure that you've answered every question with an SI unit, and if it's a vector quantity, add the direction to it. So one of the ways to improve your critical thinking and practice getting things into the right order is to look at some multiple choice questions. Multiple choice questions are there in the exam, but they are very good for practicing to check that you know what's going on and you can think like a physicist. So what do we mean about multiple choice questions? What's some of the strategies we've got to do? The first thing is obviously to read the question. I don't always read the options. I just read the given information, and I then try and not the options. Sometimes you have to read the options because that's the only way to make sense of it. I also try and identify the topics. There are times when I've looked at the topic, I look carefully at the option and then read the question. So it just depends in terms of scanning. Option first, and then the info that is given, and then you try and answer it. Very important. You should try and calculate an answer with a multiple choice question. Don't guess. You're wasting your time if you just go ABC, throw the dice. Not going to help you. If you think carefully and you do a calculation, you can be much better confident of what's going on. Now, in terms of confidence, I also want to say to you that I never encourage learners to answer multiple choice questions at the beginning of an exam because they jump from topic to topic. And so it's very important that you read the questions, let your subconscious take note of what's there, and then in your reading time you can do that, and then leave it. Answer the question that you're most familiar with first, and then allocate some time. You only need about 20 minutes, 15 to 20 minutes at the end of the exam where you're going to do all the multiple choice questions. And by that stage, your brain is triggering and it remembers what mechanics is, what electrostatics is, what circuits are. It's made the connection. And it's also been thinking in the background about all those multiple choice questions. So that's my strategy. One of the other things you can do is always try and eliminate incorrect errors if you're not sure. And we'll show you some examples. So in this particular section, what I want to do is I want to look at a few questions that are related to mechanics and also to electrostatics. And we're going to try and see a pattern here. It's pointless just learning the answer. What we want to do is to promote the skills and the thinking of the answer. So follow me as we go through these questions. So it tells me in the diagram below, they represent 4 vectors, Q, R, S, and T. Which one of the vectors is the resultant of the other 3 vectors? Now, what I hope you can see is just by reading that introduction, I don't need to look at A, B, C, and D at the moment. I can simply look at the diagram and make a decision. And so when we're dealing with vectors, we need to understand that vector addition is always done head, that's the head of the vector, and that's the tail. So we always add vectors head to tail, and you could have 3 or more vectors added head to tail, doesn't matter. And the resultant will be the one that starts at the beginning and ends at the end. It will start tail to tail and end head to head. So I'm going to apply that reasoning over here, and I'm going to say, if I do this one, I'm going head to tail, then I'm going there, that's head to tail, then I'm going back. So those 3 vectors are in order, and that tells me that my resultant vector is going to be the one that starts at where the 2 tails are and ends where the 2 heads are. This is going to be the resultant. So R for resultant. And so I can, with confidence, recognize that B would be the correct option. So please don't panic, but try and do some thinking and calculation about what the topic is. It's very important as you scan through a multiple choice question, you identify the topic. And so the next question talks about which one of the forces, so we're dealing with Newton's laws, cannot be equal to 0. So we're looking for something that cannot be equal to 0. It's not equal to 0. So we've got the normal force, the frictional force, the gravitational force, and the applied force. So in this case, I had to read the options. And so I say to myself, what's the normal force? Well, the normal force is the force of a surface pushing up on an object. The frictional force is the force of the surface that is acting in the opposite direction to the applied force. So if we had a frictionless surface, then we can make that 0. So this one can be 0, so we are excluding it. Can the applied force be 0? Yes, we can say we're not going to exert any force on this object, so let's just make that 0. So we're left with 2 now to look at. We're left at either the normal force or the gravitational force. So being here on Earth, can the gravitational force ever be 0? Well, if an object has mass, and the Earth we know has mass, there will always be a gravitational force. The universal law of gravity says that there is a force of attraction between any objects that have mass. So it is not possible for there to be no gravitational force, whereas it is possible for the normal force to be 0. This one can be 0 because we could have a situation where an object is resting on a surface, it has a gravitational force, but there is at the same time an upward force that is applied to this. And so the surface isn't pulling up, but the upward force, and that object is just suspended above the surface. Then the normal force would be 0. So I hope you can see we've thought it through and we've come to a conclusion that the correct answer is C. Let's move on to the next one. We're told here, which one of the following graphs represent the relationship between the gravitational force F and 2 objects and the distance between them? So immediately I see this. I've got force, the mass of 2 objects, and the distance between them. So they're not saying mass here. And if we looked at the graph, we'll see the graph is force and it's related to the distance. So immediately I'm starting to say, well, what's the formula? What's the law? And those are the critical questions I'm asking. And so I need to recognize that force is directly proportional to the product of the mass, and force is directly proportional to the square of the distance between the objects. And I can write D like that, or I can write 1 over r squared. So if I'm looking at a graph, I would expect if we had F and we had 1 over r squared here, those are directly proportional. And what's directly proportional? It's going to be a straight line through the graph. So just by looking at the relationship, looking at the formula for the gravitational law, I can come up with what I think the graph would be before I've even looked at it. And so what do you see here? Well, there was force in newtons, and there is 1 over r squared. And I don't even have to worry. I can see straight away, this is my answer that I've calculated. It can't be constant force. The force changes, so it can't be that one. The force changes, I eliminate it. The force here decreases with that's not true, because as the distance gets, 1 over r gets bigger, the force isn't getting smaller. And it's not that either. So we can eliminate those and say the answer is there. So the final question that I want us to look at is one which is a little bit more complex, that has 2 things. When you get these, please read the question carefully, and you'll see you've got to make a decision about positive and negative and so on. But it's about processing the information. Read the information carefully and then make a choice that's going to be the correct choice in terms of P being the positive object and Q being the negative object, because charge is transferred from P to Q. So guys, please remember that you can do this. You've just got to practice, and you've got to think physics all the time. Now that we've looked at different types of multiple choice questions, let's take a quick break, and we'll be back to look at some more questions on mechanics and electrostatics and electricity right after the break. Welcome back from your break. Let's get into doing some more critical thinking as we start to think like physicists and apply our knowledge and our skills to dealing with longer questions. So let's get going. I want to remind you that in our critical thinking model, we're about collecting data, organizing that data. The most important thing that happens all the way through is to continually ask questions in terms of making meaning. And we're going to apply that specifically to mechanics. So what are the key steps and the things that you need to know about mechanics that are very important? Always identify vector quantities. You have to define the sign of direction. Make sure you draw a sketch diagram, and it could be a vector diagram as well. So even if they haven't asked you to draw it, a vector diagram, or the alternative, just to make sense of it, what we call a free body diagram. Sometimes you'll see that that's asked in questions, but I find them incredibly useful to put all the information together. So use some form of sketch to summarize the information, present it in a different way, and by doing that, sometimes you'll begin to see and understand the principle that is behind the question. Now, one of the things that I've also discovered is that when you look at a question, the information given, instead of, particularly when you're studying, instead of going straight to answer the question, ask yourself, what questions could I ask about this given information? And if you do that enough times, you'll see that there's a pattern in the types of questions that are asked. And that will help you anticipate and prepare for different types of questions. And so after you've done the sketch and the organization of information, you're going to select a formula or select a relationship and then substitute into that equation, write down the formula as it stands on the data sheet, substitute the numbers into the formula, and then solve for the missing variable. Don't try and change the subject of the formula. This is just basic algebra, but in terms of the way that physics is marked, you have to write down the formula as it's given on the data sheet. There's a mark for the correct substitution. If you change the formula and substitute into the incorrect formula, you will lose all the marks. You'll get nothing. And then final thing, remember at the end, give your answer with the correct SI unit. And if it's a vector, it must have direction with it. And that's what we mean when we say evaluate your answer. Also check if it's reasonable. So here's a type of question that you might get asked when we're dealing with vector quantities and we're dealing with mechanics. The important thing is to identify the different given information. We've got the mass, we've got that it's connected to a 10 kilogram block, that it's a frictionless pulley, and it's all shown on the diagram below. So here is the force that is applied. So that's the force applied, 25 newtons, this is what we were given, and it's quite clear. These type of problems where you have got strings and pulleys, you must get used to those. Recognize that they're not that difficult. They relate to Newton's second law. But first of all, Newton's second law. First of all, we've got to deal with the forces as vector quantities. And so as I'm going to be looking at this question, I'm going to say to myself, I've got a force at an angle here. Let me consider what the components of that angle are and try and check that the forces all add together in a free body diagram and so on. I wouldn't be surprised if that's one of the questions. And so if we look at the question, The first thing is to say, draw a free body diagram of all the forces acting on not the 10 kilogram block, but the 25 kilogram block. So it's this block. So let me identify the forces first of all. That force is the force that was applied. We recognize that there's the force of the string, and the force in the string is known as tension. We recognize there's the mass of the object, which is pulled down by the earth. So there's the force due to gravity. There's also the normal force, which we're going to write as F normal. What we're not told is that about the surface. We're told that the pulley is frictionless, but we're not really told at this point about the surface, whether it's frictionless. So we could possibly have a frictional force over here, although we have no idea what that size is or what it is. We'd have to read more about the question, and that's always a good idea. So perhaps what we can do is we just skip on before we continue, calculate the normal force exerted, but look over here. What it tells you is that the force, it accelerates to the left, and what we recognize, the coefficient of kinetic friction is 0.15. So we mustn't forget about friction. Then there's the calculation. So if we were going to draw the free body diagram, here's the important thing. We don't draw a pretty picture of the block. We draw a dot to represent the block. Now we can start to put in the different forces. And the first force I'm going to put in is the force applied. And I'm going to label it FA. Then the next force I'm going to put in, that is there, is the force of tension, which is the string. Then I'm going to label the force downward, which is the force due to gravity. And then I'm going to label here the normal force. Now I need to be clever. I need to recognize this normal force plus the vertical component of the applied force. This one plus the normal force has to be equal to the gravitational force. So I mustn't make this one too short. I mustn't make that one too long. This red part and that need to add up to the length of that one, which I think is more or less right now. So F normal, not a very big normal force because we've got that adding in. And then the last bit, I've got the frictional force. Now I've got to decide which direction it's going to go. And that's incredibly important because look what it says. It accelerates to the left. And so accelerates to the left, friction always acts in the opposite direction to the motion of the object. So the frictional force will be in this direction and we'll write it like that. Now, if we're going to take that free body diagram and you think you're going to get full marks for it, well, you've identified all the forces, but you haven't labeled it sufficiently. What you've got to do on the side is say what each of these mean. FA is going to be the applied force, and so on. T is going to be the tension. And I'm not going to continue doing that, but I need you to understand, every time you do a free body diagram, that's what you've got to set out. You might say to me, but hold on, there's one thing that I have seen done before, and that's putting things into components. And you're absolutely right. We could take the applied force and put it into components, but then you never put in the applied force at the same time. So if you're going to convert them into components, then this is what you're going to do. You're going to need to make sure that you erase the applied force, and you're going to put in just the components. So we're going to say this component is the vertical component, V vertical, and you're going to put in this one as the V horizontal. Those are the components of the applied force. My writing isn't very neat, but I hope you can see it. You never have components and the real thing in the same diagram. Now, If we go to the actual calculation of the normal force, well, as I've indicated, that's a components question, and I'm not really going to do it, but just simply say, make sure you work out your components, because what we recognize is that there are two things that are going to add together to give you your normal. So we know VG is FG down. We know this is the component, which is vertical, and this is your V normal. And so create a vector equation, and you can do the calculation without too much difficulty. Right, calculate the acceleration of the system of blocks. Now guys, here you need to recognize that this is a typical type of question where you're applying Newton's second law, and you're going to need to solve it in terms of two simultaneous equations. So always solve it simultaneously. And what you're going to do there is to recognize the force of tension on the 10 kilogram block at the bottom has to be the same as the force of the tension on the block on the surface. You write those in terms of Newton's second law, where you're saying F net is equal to the mass times the acceleration. You break the F net down into the components that are giving you the F net, and you will have tension in both cases. You add those together by elimination, and you'll be able to work out what the acceleration is. Practice those type of equations very, very carefully. Now, this is just one long question in mechanics, but I think it covers many aspects of mechanics that you need to take note of. So please work with the mechanics and work with Newton's laws, and you will master thinking like a physicist. Welcome back from your break. Now let's focus our thinking about physics in terms of things that are not related to mechanics totally, but related to electrostatics and electric circuits. So have a look with me, some critical ideas here. So just because we're dealing with electrostatics, please remember we've still got vectors. There's the force vector and there's the electric field vector. And we need to make sure that we give the sign just like we did previously. The most important thing here is thinking about relationships and understand that force is directly proportional to Q1, Q2, and over R squared, and E, the electric field strength, is directly proportional to Q over R squared. So the relationships are very similar. In fact, what I want you to understand is when you're studying this particular section, please link it to studying and answering questions at the same time related to Newton's universal law of gravitation. So please link these relationships, although this is Coulomb's law, but you need to link it when you study to Newton's gravitational law, because the relationships are the same, and you need to be able to think through those relationships. You need to know that if you double the mass of one object, then the force is going to be doubled for gravitation. If the distance is doubled, then remember that the force becomes a quarter of what it was, because it's the 1 over R squared. And the same thing applies to Coulomb. Charge and distance, as you bring charges closer together, if you halve the distance, you're going to increase the force by 4 times, because it's the number that you're doubling, or you times 2, and you're then squaring it, which gives you 4, and then you're doing 1 over, and it goes up to the top or it goes to the bottom. So be careful about that and understand that process. And so I want you to be looking at that sort of idea as we come to this question on electrostatics. And I'm not going to spend a long time on it, but I'm just going to point out some key points that you need to take note of. So identical, that's two identical point charges. So they have the same charge. They're both positive or they're both negative. The diagram tells me they're both positive. They're placed 100 millimeters apart. Immediately I see 100 millimeters, I must think SI units. And the SI unit must be in meters. And so how am I going to do the conversion? I'm going to say 100 times 10 to the minus, this is going to be 10 to the minus 3 meters. Okay. Milli means times 10 to the minus 3. Nano means times to the minus 9. Micro times 10 to the minus 6, and so on. You need to be able to do those conversions in your sleep almost. Okay, the electrostatic force between Q1 and Q2 is 5,09 newtons. And the first thing we're asked to do is to draw the electric field pattern. So this is some book work in terms of what the electric field pattern is. Remember what that field pattern is really telling us. It's telling us if we have a positive charge, then if we place a test charge at a certain distance away, in which direction will the force be acting on that? And so you can think it through in terms of where that position of that charge is. The test charge is always positive. So we've got positive, positive. The force is going to be, because it's quite close, is going to be quite a big force in that direction. And so we can draw out the field line pattern. The field lines must never overlap. They must be continuous, and they must show direction. So if I was to actually draw the field line pattern here, it would in fact do something like this. They don't overlap with each other, they move apart, and we get this sort of field line pattern where they touch the surface of the object at 90 degrees to the curve, but they're showing you that there's going to be repulsion between these two positively charged objects. Please make sure you learn that. It's not difficult to construct it. If you've forgotten the pattern, just think, what is the field line? Put a test charge, which direction is going to go, and you can work it out. Now, the calculation. Calculate the magnitude of each charge. Here is the classic example where you're going to use Coulomb's law, Q1, Q2 over R squared. And what we need to do is to substitute the values. And you're going to say, but hold on, what values have we got? We've got the force, so we can put the force over there, 5,09. We've got the K, which we can read from the physical constants on the data sheet, 9 times 10 to the 9, if I'm not mistaken. I'll just go and check, make sure that I've got it correctly. Let's see, it goes all the way back. There we go, there's the constant. Coulomb's constant, 9 times 10 to the 9, Newton meter squared Coulomb to the minus 2. So always check back to make yourself clear, and we've got the value there. And then we need to recognize two identical point charges. So we're going to say Q1 squared over R squared, and as I said to you earlier, that's going to be 100 times 10 to the minus 3, and now don't forget to square it. And once you've substituted in, then it becomes easy. Put it on your calculator and solve for Q, okay, by taking the square root, and you'll get the right answer. In this case, we don't need to take the negative square root because we're told the values of the charge are positive. Now, the next question was about the electric field, and the electric field at the point P. Now, what you've got to recognize here is it's important that if we were to measure the field at point P, you're going to have a contribution from Q2, and you're going to have a contribution from Q1. So how do we know that they're both involved? Because it tells us the net electric field. Guys, when they give you a hint like net field, you've got to say net field, that's resultant. That means I must be adding two together. So if I'm going to go E net, I'm going to say it's the force, the electric field of Q1 at P plus EQ2 at P. Now, notice something. Q2 is 50 millimeters away, so we could do that calculation. We're going to use the equation E is equal to KQ2 over R squared. But do you notice that we could have to do that same calculation all over again for Q1? The charges are the same, but what's changed? The distance between there and there is 3 times more. So in fact, what we can say is the distance is 3 times more, so the force or the field strength is 1/9. So this one is 1/9 of Q2. And that just saves me time as I'm starting to think about the 1 over R squared relationship. Now, if you're not following that reasoning, it's fine. Substitute into the calculator, take a few minutes, get it right, add the two together. Notice in this case, they're both positive charges, so the vector line here will be adding them together. Right. Now, we want to talk about not just electrostatics, but talking about electric circuits. And when we start to talk about electric circuits, we have to identify the type of circuit given, and we've got to use Ohm's law and always try and look for an alternative method. And you'll see, if you practice circuit diagrams enough times, there are a limited number of combinations you can get. I'm just going to go through one or two just to point out some details here. So the battery that is here is connected, and there's negligible internal resistance. In some questions, you'll be told there is internal resistance, but here for the moment, this resistance is negligible. We don't know the resistance of R, so that one is unknown. When the switch is closed, the voltmeter reads 15 volts. So because there's no internal resistance, we recognize this is the EMF. This is the total potential when the switch is closed. And we can recognize that that voltmeter, that voltage is going to be split or divided. Some of it's going to be over here. Some of it is going to be between there, and that's going to be equal. Because this part is in parallel, this part is in series, and that's the main thing. If you understand what's in series and what's in parallel, this is a branch, which I'm going to call branch 1, this is branch 2, and the voltmeter reading across branch 1 and branch 2 is the same. Notice that these two are in series within branch 2. So you can see that the current through here will be the same. So please make sure you understand what's happening in terms of current and potential difference in a circuit. Very important. Guys, I'm not going to do the calculation, but I want to go to an Ohm's law investigation, which is a standard question, and there's the graph for an Ohm's law investigation. From the graph, you're asked, which quantity does the gradient represent? Now, the gradient, remember, is the change in the vertical, change in I over change in V. Now, you should remember that R is equal to V over I, but we've got I over V. So what's the gradient? The gradient is going to be 1 over resistance. And then how are you going to calculate it? Well, you measure the gradient, and then you'll be able to do the 1 over, and you'll get a value for the resistance as you've done that process. So please remember, these are important skills, and hopefully they've prepared you to be able to answer questions and prepare yourself for answering questions as you learn to think more like a physicist. I wish you all the best. From me, goodbye.